What I want to talk about today is my path to Apollo 13. We're shooting this video at Carlsbad by the sea in the billiard room. And today's date is July 21st, 2011. It's one day after the 42nd anniversary of Apollo 11 landing on the moon. And it's also 35 years after the Viking landed on Mars. I want to start with my parents. My parents were both born in 1905 in July. They both passed away in the early 1990s. Neither one of them finished high school. And they made sure that their two sons, my brother Dave and I, were going to get a college education no matter what. My dad quit school, I think it was around 16, and went into the General Electric Apprentice Corps as a tool maker. And my mother went to work for General Electric as a tube tester for radios, diodes and triodes and that kind of thing. And they, they were married in 1929, and they bought a house. And then a year later, my brother was born in 1930. And then something interesting happened. My dad's boss called him in his office. The foreman called him in. And my dad knew that when the foreman was going to call you into your office, it was a layoff notice. So before he got the layoff notice, he told the foreman that they had just bought a house and they just had a son, and it was going to be really difficult for her. And the foreman asked him, he says, "Who's financing your house?" My dad says, "General Electric." He says, "Well, then I can't lay you off." So he was spared. They put him on half-time. And my dad at the time, he had been a radio amateur for 5 or 6 years and had built his own transmitters and was a very active ham radio operator. So he marched over to station WABY over in Albany and applied for a job as a night supervisor of the transmitters. And I hired him on the spot because he had that direct experience. So he worked half-time there and half-time at GE and was able to get by, and he was kind of proud of that. Now my brother, he started school about age 4 1/2, and I was right behind him a year later. And he was the valedictorian. He got straight A's all the way through grammar school. We just had one building, kindergarten through 8th grade, and it was a good school, I felt. But my brother was the A student, and I wasn't. And every time I walked into a class, the teachers were expecting that we're going to get another A student. They didn't. They were a little disappointed. So my brother then he goes on to high school, and same situation. He's the A student, and I'm the B student. But I did well in math and science, so I applied at Union College in Schenectady in the engineering area. And my brother was a year ahead of me, and my brother Dave, and he went into pre-med, and he entered there in 1947, and I went in 1948. He graduated in pre-med in 1951, and I graduated in 1952 from engineering. And he went on to McGill University in Montreal in their med school and graduated 4 years later at age 25. And then he went into internship, I guess we call it. Then he did several years, 3, 4, 5, I can't remember how many, in the Army as a orthopedic resident. And then he left and went into his own private practice, and he lives in Northwest Indiana. When I got out of college, when I graduated, they had a lot of interviewers come to Union College. Everyone that interviewed me gave me an offer, and I had offers in Saudi Arabia, Alaska, Columbia Gas and Electric in New York State. And then I had 3 on the West Coast, the aircraft companies, North American Aviation, Lockheed, and Boeing. And I always liked the North American planes better than anybody else's. And there was always that, there was an advertisement about Long Beach, and I could just see the Long Beach and all the things that go along with a nice beach atmosphere. So I picked North American Aviation. In a few days after I graduated, I was on a plane with a friend who also took a job at North American. The two of us flew out to Los Angeles, and we rented a room in a home and stayed there. And I got into the hydraulics design area, and they put me through 2 weeks of drafting, which I thought, boy, this is a big waste of time. You know, here I got all this mathematics and physics and chemistry behind me. I'm here drawing lines on paper. It turned out later on to be one of the most valuable things that I learned, that whole drawing system and how you get things done. So I did 2 weeks in there, and then they put me in the hydraulics design area where they assigned me to the right-hand engine bay at the F-86H. And I had all the hydraulics that were in that, and the drawing for that was longer than the pool table here in this room. And I worked on that for several months, and then I saw an opportunity to go into research lab, and that's where R&D was more what I wanted to get into. So I went into the research lab and I did some structural analysis and backup on testing and things, and also hydraulics. And I had quite a bit of hydraulics experience, both in hydraulic systems and fuel systems, and did a lot of research work on hydraulic fluids for the B-70 and the X-15. They didn't have the characteristics for those fluids, so they wanted to know what's the shear stability, thermal stability, adiabatic bulk modulus, viscosity, over the entire range of pressures from 0 psi to 6,000, and from minus 65 degrees Fahrenheit to 600 Fahrenheit. 450 for the X-15, but 600 for the B-70. So I had to characterize and measure these characteristics, and I had to design the experiment to do that. There was nothing you could go out and buy and do this. So that was fun doing that, and I learned quite a bit on that. But as time went by, I worked on quite a bit on the F-100, big input on that, a little bit on the X-15, quite a bit on the YF-108, which was in competition with another. This was a Mach 2 plus fighter, and supersonic transport. But after 10 years in North America, I couldn't see that I was getting anywhere, so I wanted to get into the space program, and the closest I had been to that was the X-15. So I applied to a company called STL, Space Technology Labs, and the reason I applied to them is I attended a lot of lectures at local universities, UCLA, USC, and some of the hotels that lectures on space. And some of the real prominent speakers were these scientists and engineers from STL. So I thought, this must be a great company. So I applied there. And at the time, they were only hiring people with advanced degrees. But by that time, I had a BS in civil engineering and an MS in civil engineering. And I had all this valve experience, which they were really interested in hydraulics. So they hired me, and I was shortly assigned to the LEM descent engine, the Lunar Module Descent engine. And there was just a kind of a handful of us, and we were competing against the giants, which is rocket nine. And when I was assigned the flow control valves, I'll take a picture of it here. I had actually the thrust control assembly, which included the throttle actuator, the mixture ratio control, and these two flow control valves. And that's what I worked on for several years, and that was in order to design those valves, I had to understand the characteristics of the injector and the throat chamber, because it was an ablative throat, which meant its resistance would be changing as the throat got larger. So we had to find some way of decoupling the flow control valves hydraulically from everything downstream. So no matter what happened downstream, it would not affect the flow of the propellants. And the way we did this is we experimented with cavitation. And what that means is we bring the flow into the flow control valves and meter it down to a level such that the velocity is so high that the static pressure drops down as low as it can, which is the vapor pressure of the propellant. So now what that means, you've got a fixed pressure drop over this spot. You've got the inlet pressure and a vapor pressure, and no matter what you do downstream, that pressure drop is fixed. So the only other things that can vary the flow is things like temperature, which is kind of fixed, and the aperture in the flow control valves. And it's an annulus flow path, which is a very thin annulus. in that it was sized such that we could throttle over a 10-to-1 ratio, which is, this engine was designed for 10,000 pound max thrust, throttleable down to 1,000. So we used the propellant combination, which was hydrogen tetroxide, N2O4, and a Aerozine 50 was the fuel, and that was a 50-50 blend of N2H4, which is hydrazine, and unsymmetrical dimethylhydrazine. And those two propellants are hypergolic, which that means they ignite on contact. You don't need an ignition source. As soon as they contact, you get ignition. The mixture ratio was the important characteristic of these two, of this engine. We had to hold 1.6 oxidizer to fuel weight flow rate mixture ratio. And it's the way, with this metering that we had on the flow control valves, it was very easy to accurately meter the propellants and hold that mixture ratio. And the problem is, if you go off the mixture ratio, the thrust will go down, because now we've picked 1.6 as the maximum or the optimum mixture ratio. So not only do you get your propellants unbalanced, but you also lose a little thrust, and that's important when you're coming in, landing on the moon, and you only have a few seconds left. You want to have that. And as I worked and developed the flow control valves and the thrust control system, I mentioned earlier that I really had to understand the injector and the thrust chamber. So I got to know the engine, all aspects of it, and I was in on all the testing. I was in on the design and all of the testing, which was done in back of San Clemente at the rocket test site there. So as time went by, I kind of inherited the whole engine. I was the lead engineer at the time that on the LEM descent engine at the time of the first lunar landing, which Apollo 11. And so I was assigned to go to Houston for Apollo 11. I had this Apollo 11 flight plan that was useful in tracking the minute-to-minute operations of the flight. I sat in front of a monitor, a computer monitor, and I don't know if the camera's going to pick this up very well, but the lower right-hand section of this monitor was the propulsion feed system and the rocket engine itself. So I could sit there and follow all the characteristics of the performance. I could see the inlet pressures, the propellant feed system, the flow control valves. I could see the thrust chamber pressure, which is really the important thing. If you're getting the thrust that you're expecting, that's great. I could see the mixture ratio, and in addition to all that, as we're coming in for a landing, I had all the dynamic information on rate of descent, altitude, forward velocity, velocity and direction of the flight, and all that information available there, so I could see. And on top of that, I was wearing earphones, and I could hear the astronauts and everything else going on between Capcom and the astronauts. The thing that I did miss, though, is the medical information in the propulsion room that I was in, and for a good reason. And what would we do with it? In the meantime, between operations, I would go down into the press area, and they'd have these change of shift briefings, and I'd pick up all this material. Like on the billiard table, I have the lunar tracking map, the Earth tracking maps, and everything else that you'd like to know about the flight. So I got quite a collection of those. Then, of course, the Apollo 11 was a very successful flight. Of course, it was quite a responsibility that Neil Armstrong had, because here he was in the descent module along with Aldrin, and they were coming in to land, and it was all computer controlled. And as he's going across the surface of the moon, he could see this boulder field that the computer was going to take him into. And at that point in time, he's decided he's not going to abort. He's going to grab the controls. He's going to now fly it into where he wants to land. which he did do, and very successfully sat down the vehicle on the surface of the moon. And what's interesting in all that, when he was in the LEM setting it down, he said he couldn't even feel the touchdown. It was so soft. At the time of touchdown, it was a zero velocity descent just prior to touchdown, which means he really had that pinned down good. And I was thinking it was like 30 years later, it was July 20th, it'd be 1999. He was being interviewed by a C-SPAN, it was. And there were 4 other astronauts being interviewed, and they were asking each of them one by one what they thought was the important development in the Apollo program. When they got to Neil Armstrong, he said it was the design of the bipropellant cavitating Venturi valves. And I knew why, because he took, when he was coming in for landing, he was moving those pinions in the valve back and forth so gently to come down for a soft landing. That and the precision of the thrust control was really impressive. Apollo 12 was next, and that one went like a charm. And then Apollo 13 came, and I think I was at USC in night school at the time, and I was working on an advanced degree in mechanical engineering, which I received in 1972. And I was pulled out of class by one of the security men. My boss had called Joyce, and Joyce called USC, and they pulled me out of class and said, I can't remember how much detail I had. I already had tickets and everything to fly because I was going to be there for the landing. So I got home, gathered my stuff together, and got on the next plane. And when I got on that plane, I got to thinking, I'm the guy, and I'm thinking, what's the worst thing that can happen? And I was thinking all the way through the engine from the beginning, the fuel into the main shutoff valves, through the flow control valve, through the injector, through the thrust chamber, through the expansion cone. And the only thing that seemed like it would be a danger would be the thrust chamber, because that had an ablative liner, and that's something that does deteriorate with time. The thrust chamber itself, which is this part of the engine, from here down, and this is the nozzle extension. This is columbium. The thrust chamber is titanium, but it's got covered here with some insulation. In the inside the thrust chamber is about a 2-inch ablative liner, and that's material that just erodes as you burn. It's an insulator, and it carries heat out, and it protects the titanium case. And it was not a problem at all for any of the Apollo landings, because you fire the engine for about 10 to 12 minutes, sets down, and you never restart it. You don't have to. You shouldn't. You can't. If you did, you wouldn't go anywhere. But in this case, we knew that we had to restart the engine after a long burn. So to get into it, what happened, they had an explosion in the service module in this region here, where the oxidizer tank blew up, and it essentially rendered this whole service module inoperable. At the same time now, because of the explosion, they've lost their reference to the stars, the moon, whatever. Because here it's now tumbling in space, and their alignment platform on here is now gone. So now, how are they going to align this vehicle? This thing here is now tumbling in space. Not at a rapid rate, but it's not following any nice trajectory and in a nice form. So they decided they would use the LEM descent vehicle, their alignment platform, and their guidance system to now guide this whole apparatus. You've got the service module, command module, the ascent stage, and the descent stage. You got these 4 pieces. This part, the descent module, weighs about 33,000 pounds. And this part, the service module with the command module, weighs about 60,000 pounds. So it's close to 100,000 pounds of mass tumbling in space. And this little engine there has to now control it. It's on a 10,000 pound thrust engine, max thrust. The service module engine is a 40,000 fixed thrust engine. Yeah. Yeah, the Apollo 13 now is tumbling in space, so they use the LEM descent engine alignment system and guidance system to align the vehicle, and they computed that like a 30-second burn on this engine would put it in a free trajectory, so now it would loop around the moon and head back toward Earth, knowing that they had corrections to make and the long burn of this engine to get them back in time. Now, the real problem was they're now heading back toward Earth, but they don't know yet, do they want to land in the Pacific Ocean, they want to land in the Atlantic Ocean? And what are the resources in the Atlantic Ocean? What's the resources in the Pacific Ocean? And what's the weather in both places? And at the same time, they're running out of oxygen, but they're working on that problem. So you want to get these astronauts back as fast as you can. But here's the Earth turning like this, and you want to land. They decided the Pacific Ocean, so they know where they want to land. So now they got to get the right burn, get them back early enough, and still hit that spot. So they burned for something like 420 seconds in that order, and then shut down with an idea about a day later. They knew they had to do a mid-course correction. They kept on throwing different profiles at me because they didn't know which they were going to do. And I had to evaluate each of them from a thermal standpoint, because that was the only issue that came up, was the thermal. And so I had a guy in Redondo Beach that was ready to take any profile I threw at him and load it in the computer and then compute for this blade of liner, was it going to char through or not. So now the idea, what we wanted to find out was from the thermal analysis, did we char through? Because if you charred through, we knew that after about a day's coasting, that material would all cool down and crack, shrink and crack. And now if you restarted it, the hot gases would then go through that crack, through the chamber, and then you'd lose your mission. So the engineer that I called back there, he ran the model, and he said, no, you've got a good half-inch virgin material, so there's no problem. And I said, I want a confirmation. I said, I can remember that we ran a test at the Capistrano test site in back of San Clemente, that the stand valve failed closed too soon, and it shut down the engine about that same duration. And I said, I wonder if we still have that chamber. Could you call the test guys? Could you find that chamber? And they did. They found that chamber, and now that they found the report where they sectioned it, and they confirmed that there still was ample virgin material. So then, with that information that I told them, then asked the people, we got a good go on this one, we don't have a problem. So we went ahead, fired the engine, and then in the actual burn on the billiard table, there is the oscillograph of that particular burn, of that second burn, that long duration burn. And it was when I looked at the oscillograph, I was amazed at how smooth the thrust chamber pressure was on that. It was a good run. So that took care of Apollo 13. Everyone was very pleased with the results on that, because the mid-course correction worked out fine. And then they did another very small correction, I believe, with the attitude control system or the reaction control system, and brought it in at the right angle, the right spot. And it was interesting that it took them a lot longer to get through the atmosphere, and everybody was kind of sweating, because when they expected it at a given time, it was several seconds later that they finally showed up, and it was really quite an experience.